Welcome to the third project for the Physics 1010 class. We will be doing an experiment to test Archimedes Principle, which states that the upward buoyant force acting on an object is equal to the weight of the volume of the fluid that the object displaces. Mathematically, this means that the upward buoyant force is going to be equal to the acceleration due to free fall times the volume of the displaced fluid, which is going to be equal to the portion of the volume of the object that is immersed under the fluid, and times the density of the fluid. Now here I have a setup. I have a pot full of water and I have a container placed inside of it. I have a number of cans and containers of different masses. I've already measured each of those masses. I'll be displaying the masses of each on the side. I've also measured the diameter from the bottom of this plastic container. It is not perfectly cylindrical, but it is good enough for our experiment. So what we are going to be doing is we're going to be placing each of these objects inside of the container. We're going to make sure that it is horizontal on all sides. Then we're going to grab a permanent marker and we're going to try to draw a line. Now I'm instead going to draw 3 dots and then connect the dots as a line later, since I found it to be simpler. So for this one specifically, it's going to be here, here, and here. Then I'm going to take the container out and I'm going to draw the dots later over here. Now I've already done the experiment ahead of time for the other objects. This is mostly for illustratory purposes. I will be displaying an image of which watermark corresponds to which of the objects, and I will have a ruler next to it showing how high it is from the bottom. What we care about is the distance from the bottom of the container to the water level, since that is going to be the depth of which the object is immersed in the water. Now that we've done our measurements, let's move on to Excel. So here we have the density of the water is going to be 1,000 kilograms per meters cubed. The acceleration due to free fall is going to be 10 meters per second squared. The bottom diameter of the plastic cylindrical container, which we ourselves have measured at the beginning, is going to be 0.180 meters. And the mass of the cylindrical container is going to be 0.070 kilograms. Now, as you can see from the table, we have split the data based on the trial, where the trial we have distinguished on which object we have placed inside of the container. So we have the mass of the placed object, which is the mass of, say, the small jar or the tuna can, like corresponding to it. And to calculate the total mass, we have simply added the mass of the cylindrical container along with the mass of the placed object together. The units are in kilograms still. The depth at which the container was on the water was measured in meters. That's in the 4th column, and then to calculate the weight of both the container and the placed object, we have simply used the total mass and we've multiplied that by 10 meters per second squared. And we have gotten the values in the 5th column. One thing to note is that the depth of the container the depth of the container that was submerged underwater was increased alongside the weight of both the container and the placed object. So this is important because the actual weight of the object does not depend on the depth at which the object is submerged underwater, or the portion of the volume of the object that is submerged underwater, but the deeper the object is submerged under the fluid, the smaller the apparent weight of the object is, at least up until the object is fully submerged. This is because the upward buoyant force caused by the water particles pushing up on the object decreases the weight one must counteract if they try to lift the object to the surface. So the actual weight of the object does not change, it's just how much you have to push it by to lift it upwards. Then to calculate the upward buoyant force, this actually is a bit more involved. We have simply multiplied the density of the water with the volume of the with the portion of the volume of the object that was submerged, along with the acceleration due to free fall. To determine the volume, because it's a cylinder, that's simply going to be the cross-sectional area of the cylinder along with the length of the container that was under the water, or the depth. To find the area, we have simply done pi times the bottom diameter of the container, like the square of that, and then we have divided it by 4. We have obtained the following results. So for example, the small jar, we have that the weight of it is 1.8 newtons, and the upward buoyant force is going to be 3.1 newtons. Lastly, I have plotted all of this. I have plotted a graph of upward buoyant force against weight, and I have done a regression analysis for a linear equation. And what we find is that there's a strong correlation between the upward buoyant force and the weight of the plastic container along with the object. I have forced the graph through 0 because ideally, if the object has no mass, then there's nothing that there's no object that the water particles can push. So the upward buoyant force is going to be 0. So I have forced the graph through the point 0 y-intercept, and we have determined the slope of the slope of the linear function. We find that the slope is about 1.0929. This is going to be unitless since it's converting newtons into newtons. And what this is about equal to 1. It's not exactly equal to 1. I assume it's probably because the container was not cylindrical enough. So that's why there's that small bit of deviance from 1, but it is fairly close, and it shows that the weight of the plastic container in the object was about equal to the upward buoyant force. This does show experimental evidence that Archimedes Principle holds. Now, I have explained what Archimedes Principle is, but I have not explained what we mean by the upward buoyant force. The upward buoyant force is a consequence of how, in fluids like water, the deeper an object goes from the surface of the fluid, the higher the pressure exerted on the object. For points on the sides of the object that are at equal depths, the forces due to the water pressure exerted perpendicular to its surface cancel each other out, since they have the same magnitude due to the equal pressure and area of application, but are pointed in the opposite direction to each. However, the points at the bottom of the object are deeper than the points vertically aligned at the top of the object, and as such have a higher pressure exerted on them from the water. This means that the force due to water pressure at the bottom is going to be bigger than the force due to water pressure at the top. The net force upward of all of these forces is going to be equal to the buoyant force. Thank you for coming to my video, and I hope you guys have a good day.